LK99 room temperature superconductors were a huge deal last summer. It was all over the media, but then everyone said it was over. But it's back now with the original team releasing big results yesterday, but we still don't know many things. So here we're going to review what we do and don't know and how we got here.
And he's Brian Wang. I'm Randy Kirk. He's a scientist. I'm not really. And Brian tries to explain things to me in a way that I understand them. We broke this news. Brian and I had multiple videos. He put it on the big nextbigfuture.com blog site multiple times last summer when everybody was talking about it. It was headline news, this massive breakthrough that could change everything about electricity. But then folks were like, is it a fraud? Are these guys crazy? Maybe it's just a game, and it kind of started to recede. But there was one guy, Brian Wang, who continued to believe in these guys. And he continued to report on it. And nextbigfuture.com had article after article. We've posted multiple articles here on this channel. Brian, okay, let's talk about what these guys reported on yesterday. What's the good news? What's the we're not quite sure news? And then what is it? How does the future play out?
Okay, so let me share my screen. Okay. Okay, so here's some of the main points from the thing. They only had a 10-minute presentation at a major physics conference, the American Physical Society conference in Minneapolis. So it's one of the largest, most respected conferences in the world. But they only had 10 minutes, and they were put into a small room. So the presenters didn't say, okay, this is a huge event where it's going to be groundbreaking. So the major parts of it is, they can see here on the left, there's a little photo showing that the little piece of a fragment is not touching the magnet that's over. Superconductors, if you have a full superconductor, it has something called the Meissner effect, where basically you have a superconductor floating over another magnet, right? Yeah. So that's something that can be shown for other superconductors, but the other superconductors have to be at really low temperatures, like 200 degrees below 0 Celsius or something like that, get really, really cold. And they also have things called locking effects, where you kind of move it and then it kind of like snaps into another position. So that was what the video on the right was trying to show, that there's some kind of like locking effect. So those would be two smoking gun kind of effects for this. So we have two smoking gun effects. The issue is that the full levitation is not as high as you would like. You would like a stronger effect with there, but it's kind of pregnant, right? So it is floating. It's no longer partially levitating, which before only, it's like this one on the right is partially levitating. It's touching on one side. Right. So it's not fully levitated. So they're showing full levitation and partial levitation, right? Where it's like I'm standing on one leg. I'm not floating above. So the difference between standing on one leg versus I'm a yogi genie floating in the air, there's a difference. And the question is like, well, how high are you floating? I'm floating, I'm not touching the ground. So that's kind of a big deal. So here again, we see another photo of it where it's zoomed in on a video. It's a very tiny fragment. It's like zoomed in like 100 times. So it's a really tiny fragment. But again, you can see there's a gap below, right? That yes. It's floating above a magnet. It's not touching, right? So that's the kind of like the biggest deals from this thing. There were a bunch of people went to the meeting, so they got full up, but it was a small room, right? So they said the magnification of the thing was like 1,600 times. So it's like a really, really tiny thing to see this thing. The other thing was say it was done by the Dae-Si Jung, the name of a Korean person, in the SCT lab. So why is that relevant? So this is also showing the flipping of it, saying that it's not this other magnetic effect, because the people said it didn't work, said it was not superconducting, it was another magnetic effect. But they say that because you can't, well, flipping does not occur, that means it can't be this other method. So again, in this slide here, up in the top right, you see SVT lab, DC Jung, MG Kim, replication. So these, the guy who's presenting is from the quantum ERC lab, energy research lab, and then the Korean lab. And then DC Jung and MG Kim are other Koreans at a different lab. So another big call out was that the critics said, we have not had other people experimentally replicate what you guys did. So then we think that you guys made a mistake because other guys can't replicate, because that's a big thing of science is other people have to be able to replicate. So now in Korea, they've said we have other people replicating. There's also groups in China, about 10 groups in China that are replicating. So, but only 2 of the major labs, Beijing and South China University, have said they replicated, and they have not done all of the floating bits of material part. They've done detection of magnetic aspects of the Meissner effect. That when you get the suspension floating, other things are happening. Hysteresis loops, other things are happening that they say indicates superconducting. Also, things like microwave absorption. So basically, they can do other tests that show that they can detect the smoke of the smoking gun. Right. Mm-hmm. So that's what they can do with this thing. The other thing in this slide are other measurements of voltages and resistance and that kind of thing. That is not as convincing a set of readings on that. It's because it's not, it's a 0, but it's at a very poor equipment, right? They're not showing that it's like, way, way better than copper, because the number 2 slide in the middle there showing copper foil, and it doesn't seem to be like, 1,000 times better than copper, which it should be if it's a superconductor. The reason, I wasn't there at a short conference, but based on the other material that's gone before, it's because they don't have enough of the material superconducting. They only have a tiny flake, and it's not all superconductor. So then a bunch of it is still lead, which is not better than copper for conducting. So you get not great readings off of that, right? But if you have enough to do these other effects, like all the people who said, okay, it's just sulfur contamination.
Right.
I'm not sure about you, but I have never seen sulfur floating over a magnet. Admittedly, I haven't tried, but like people don't have these things. Like, look, I got my sulfur thing floating over a magnet. It's almost a superconductor. That doesn't happen, right? So the problem with all the people who are criticizing it say, I think I can make this chart of resistance readings doing another way. Well, that's great. That's wonderful. You did made that chart, which is not that good a great a chart, but you did not make the thing float, which is kind of like the whole, one of the key things about why this thing is so interesting. So those are the main things from this conference. So
let me see if I've got it right.
Yeah.
Okay, so we have 3 things at least right now that are pointing to this being potentially at least a solid case of the kind of a product that might be a superconductor. So we have the fact that it did 100% float. This had not been shown before, and this is now shown. It was really close last time. This time it's completely floating. So that was good. We had the inability to flip. So they took some tweezers. They tried to flip it. They showed that it wouldn't flip. Because it couldn't flip, that would be another example. We've got the Chinese lab saying we've tested it a couple of other ways. And they've made their own version of it.
Right.
And so it's them replicating the actual product and saying, we haven't tested it on the floating aspect. We haven't, you we haven't tried to flip it. We haven't done those things, but we've used microwaves and other methods, and we say it looks good. The remaining problem is that we're not showing actual superconductivity in terms of moving some kind of electricity along this product that then works better than copper. So then my question to you is, why not? What does it take to, you said it doesn't, you don't have enough of it.
Yeah.
And in the past, you've described to me anyway, like if you had a pile of sand, it's like if you had a pile of sand, if you compared it, and you would have one grain of sand in there that would be this.
Yeah.
And so it's hard to find. It's like finding a needle in a haystack. It's really hard to find the one piece of grain of sand that has this effect.
Right.
And you'd have to find lots of them. So why can't we find lots of them and stick them together and make something that's large enough to test?
So it has to do with the nature of what they're doing is one-dimensional superconductivity. So one-dimensional is like a hair, but actually a hair is thicker, so it's beyond 100 times, 1,000 times bigger than that. So it's like I'm going down one little string of things, and at each section I want the copper in the right spot. So then I got to get
copper in the right spot. So this is the nature of this molecule. Is to explain that.
So like it's got like 2 rings of lead or something like that, and say there's 6 positions on it, right? So then if I have like a combination lock, I want to like dial one position to number 1, next position number 1, and if the position that number 3, number 4 too much, then it disrupts the wire. I don't have a continuous wire of superconductor, right? I have to molecularly get everything to align. So then the problem there is that, so the advancement that they made was instead of doing the old material, they added in some sulfur. So they put sulfurs in the spots. I don't want my copper going to these spots. I'm going to stick sulfur there. Okay. So then I've improved my chance of getting it to work by, say, 5 times. Okay. Because I've blocked out where I don't want you to be. But then I need to get the alignment problem. So maybe I have to do something else with the chemistry so that it always lands the right way. You could put feet onto the molecule, just hypothetically, so that it lands like a tripod, where it's like it only lands one way. Okay. Right. And then you can get everything to align, and then that chain will always be good. So they have to do some chemical stuff to make everything line up perfectly every time. And they haven't got that quite there yet. Although the area where they did get the good readings, 1,000 times better than copper, was for thin film. So I make a little bit of it. So I take a little bit of it and I smear it across like sunscreen or something like that across the surface, right? And then this film is now very narrow. So now the single bits of one-dimensional stuff, there's less ways they can jumble up because they're on a 2D surface. Right. So now I've spread them all out there, and they got supposedly in one of their patents said they got 60% on my thin film to be good, to be superconducting at that low resistance. Why would that be good? If I could get 100% on the thin film, then I could make a computer chip, right? Okay. And computer chips with superconducting can be, instead of 4 gigahertz for my regular chip where we've been stuck at for like 20 years, you can go to 800 gigahertz, which is what we're trying to do with some other superconductors, right? And the low power voltage, all that stuff would work fine. So that goes to why would this matter? Is because if you can make it work with thin film, make it work 100%, make computer chips out of it, then we can get computers that are 200 times faster.
Oh, I see.
Now, initially, it would, if I just barely get it to work, maybe only making 1 or 2 devices on there, or maybe get to 1,000 devices versus 100 billion, 1 trillion in my iPhone, right? Because we mastered working with silicon, right? This thing is new. We hadn't really mastered it. But if I only make 1 or 2 devices that I don't have to cool, these devices are so powerful and so useful, I can detect magnetic fields, 1,000 times, 1,000,000 times better right?
Mm.
So they're immediately useful just by making one device, one Josephson reduction, a squid device to detect magnetic fields. Things like better MRI, other kind of sensors,
Oh,
right? So you can make sensors worth, millions of billions of dollars, millions or billions, not millions to billions, but quite a substantial, not insignificant amount of money by doing that. And then if I make 100,000 or a million things on a chip, it's not going to outperform 100 billion chips on a iPhone, but for some applications like magnetic, radar or terahertz radiation things, where I'm trying to do signal processing for communications or something like that, then it could be very useful, right? Where I'm like, I need to process all the signals and then up the bandwidth rate on my wireless communication, 100 times, right?
uh-huh.
So there's a bunch of things where even moderate level capability of this thing would become transformational. So if I can get communication speeds up 1,000 times, that's worth trillions of dollars.
Gotcha. Gotcha. Yeah. Okay. So then at this point, they've got some scientific proof,
Mm-hmm.
but they don't have a product yet. So
Right.
they have is the next step maybe almost as hard as the first step, which is how to get a consistent product that they can actually extract from the pile of sand efficiently enough so that it is actually usable.
Right. You have to get at least lab reliability. So you have to get lab reliability, but they're not motivated to give all their secret sauce
Uh-huh.
away,
Yeah.
right? To everyone, to say, you don't believe me. I'm so hurt that you don't believe me. Here, let me give you everything that I know and do about this thing, right? Because they want credibility. They don't want to be, seen as fakers, right? But if they prove everything and they win the Nobel Prize, the Nobel Prize is worth $1 million.
Right.
If they prove everything on the commercial side and they make that work, that's billions of dollars,
Right.
right? And supposedly they're already talking to and working with IBM,
Okay.
right? There's other companies who say, I believe you enough that we're going to try and make this work, because
Right.
the whole superconductors themselves, even though you have to freeze them so much, is already worth $4 billion. We use them for some levitating trains. We use them for magnets for particle accelerators. There are applications that we use them for. And if I didn't have to put in $1 million of cooling for every application I use,
Right.
I could then use it for many more things that worth a lot of money,
Sure.
right? Back when 20 years ago, when we last made an advance in superconductors, up from 10 degrees, 20 degrees above absolute zero, up to 70 degrees, 80 degrees above absolute zero, going from liquid hydrogen to liquid nitrogen, 10 times, 20 times lower cooling cost. The scientists who did that gave a incorrect research paper to a major journal
Oh.
because he said it was called YCBO. He said the Y was urbidium instead of yttrium or something like that. He gave the wrong one because he was still applying for a patent
Oh, I
on
see.
it. So then he got the patent cleared, and then he called up the guys at research paper. Said, oh, by the way, make an edit in 30 spots. I gave you the wrong. I typoed in the wrong chemical thing. It's Y, not YB, right? So he was willing to mislead people in order to make a few
Sure.
$1 million,
Sure.
right? So it hasn't been unheard of in this particular field for that to happen. And so the way science and commerce work is that this is hugely valuable. So they're got enough attention to get millions of dollars to support their work,
Right.
and they're gonna get more. Here's how I see things going. The China researchers, they believe, and they're working on it, and they have made progress, and they think they're ahead of the Koreans. So there's 10 research labs. The Chinese guys are going to be issuing new patents, and they're going to be issuing new papers soon. So that's the rumors and the buzz that we hear from them. The Koreans will continue to do their work. The US has small levels of funding that I know about, from the Air Force Research Lab to like a university, a small university. And they have had some researchers doing some work on it. If China is pushing this ahead, and if the results are kind of interesting, like they're getting close to something, then the US has no choice.
Right.
DARPA, Air Force Research Lab. DARPA is the defense research projects. They get about like $3 to $4 billion per year. Air Force Research gets more. They get like $8 billion per year. And the Navy also has the research thing. So the US military, like I said, the better radar, better communications and stuff like that, they totally want that stuff. And they're willing to try crazy, crazy stuff to make that happen, right? So them failing on research, they don't care.
Yeah.
Right. So, they spent like tens of billions of dollars to make the stealth coatings on their planes work. Right. So for this kind of thing where they could get better radar, better stuff, and the risk that China can get it and they don't.
Yeah.
They're going to have tens of millions of dollars in this thing, maybe hundreds of millions of dollars on this thing. And all the scientists who say, I don't believe this can work, blah, 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 they won't get the 10 to 100 million dollars from the research that the military can put in. When the military dumps the money in, only if you say, not only do I believe it, I think I can make it work. They're the guys who are going to get the money, right? So there'll be a bit of a tune change within that, but it'll be more on the low key because they only need to talk about that to the DARPA and the Air Force Research and the Navy research funders, right? They don't have to go out to the public and say, I believe it, because one, this is going to be, it could end up shifting to be a dark project, right? So, so that's how I think it happened, that there will be a lot of work, millions of dollars spent to achieve these things. The work won't be easy. It's a, difficult things to make these things work at scale. But other things in superconductors haven't been easy either. Like they stick things between diamond anvils to try and crush things together. They're trying to make the diamond have sensors on it so they can detect what's inside the thing. So they're going to heroic levels to try and make better superconductors. And the fact that they got to work on some chemistry and to search through a million options, that's nothing.
Wow. Okay. So we're looking at probably years before there would be something commercially happening on this, but it is evidence that paying careful attention to what's going on with this has been a wise decision on your part.
Right.
And so what do you think happens next? These other papers are going to be some peer-reviewed papers are coming, I think, from the Koreans, as well as the Chinese. So that'll be the kind of next thing we're looking to see.
There's also some non-peer-reviewed papers that should be coming out. I think the SAT labs or the Koreans are supposed to be putting out to archive, ARXIV, which is non-peer-reviewed papers. They put out some methodology papers about what they did to make certain stuff. So they want to give away some secret sauce just to let people know some basics of like, here's what we're doing 6 months ago or a year ago, and now we're willing to share it in more detail. So there'll be more of those papers coming out, but the bigger ones would be the patents and the peer review papers, because that potentially can move stuff. I'm really hopeful that something should come out of the thin film. So if they can get the Meissner effect full levitation completely solved, that is definitive.
Right.
Then there's like no question. There's no other thing that does that. So that would be definitive. So they kind of did show that. So that's close to, on the definitive side. But then also the resistance, getting the thin film, getting some form of it to be, 1,000, 10,000 times better than copper.
Right.
That's also definitive. So those are the things where it's like, okay, it was hard. Now it's done. Getting it, other people convinced of it. Then all the media, everyone will say, okay, we all believe it's all happening. All the scientists say, yes, it is happening. That although some people, while the effects are a bit weaker, could still have complaints, but then they'll just be difficult at that point. They'll be in the minority at that point, right? So that shift in tone could happen over this year. It could be another summer of big announcements where patents and the definitive full levitation thing, because right now I think a lot of people are still brushing it off. But if the National Research Lab, like Berkeley, those people say, okay, yeah, this is it, then because I think Berkeley is doing the most simulation with their supercomputers on it. So if some of those guys come out to say it, but if how eager they are to say it is less clear, because if they get $10 million, $100 million from DARPA and the Air Force Research Lab, they don't need to go broadcasting out, hey, yes, we're working on it now, right? Because they'd be in competition with China. Right. So there's a bit of that kind of stuff. But at a certain point, they'll moved on to enough. So yes, okay, yeah, it's really working and we're doing it. Which may be, I think, toward the end of the year or next year. It could happen earlier in the summer if enough of this stuff happens, but it's not certain.
All right, so you've heard it here first. You heard it here last, and of course, it's the blog, which is where things break the fastest. You want to head over there. If you're not subscribed over there, you should go over there and get subscribed so that you're getting those alerts when Brian puts up absolutely the hottest science, and not just in this world. I mean, in the EV world, in the biological world, in the, one of your favorites is living forever, right, Brian? I mean,
right, yeah.
Elon Musk says that doesn't sound like a good idea to him. He's looking forward to the peace that comes with death. But anyway, tons of really cool stuff over at nextbigfuture.com. Any last thoughts?
No, look forward to exciting new developments for all kinds of technology.
All right, we'll see you another time.
Thank you.